So this is our product webinar session 1 for Entity Resolution Basics. And this is going to ground us in the fundamentals of Senzing Entity Resolution. So we're going to look at the definition of entity resolution. We're going to watch some fun animations around that. If you hadn't seen these before, they're in your study packet. We're going to cover data and what's needed. We're going to talk about the entity resolution process in slow motion. We're going to watch a video around that presented by our CEO, Jeff Jonas. And then we're going to spend, I'm hoping to spend the bulk of our time talking about the basics of how records are processed to create entities and link relationships. So entity resolution is fundamentally about accurate counting. You know, is it 5 people with 1 bank account or 1 person with 5 and so on, right? So if you can't accurately count, you can't estimate a direction or speed or make a prediction about what's going on, right? So that's the goal of entity resolution. So why does that matter? So transformational capacity can be unlocked with a real-time understanding of entities, their relationships, and the ability to trace their transactions across data sources. So what I've put underneath here is just a sketch of what becomes possible. So that's why it matters. And entity resolution problems can be found anywhere that you need to match records across data sources to create ultimate views of entities, whether they're people or organizations or things like vessels or servers or something else. And you need to understand those relationships, and you need to have that picture evolve as new observations are seen. And that's the fundamental function of the Senzing product, is to give you a way to do that quickly, easily, and at a lower cost than perhaps a roll your own approach to entity resolution.
Lesson 1, Defining Entity Resolution. What is an entity? In data, records often contain information about real-life people, places, organizations, as well as things like servers or vessels. These are all examples of entities. Entities can be any noun you care about that have information in 1 or more records in your data sources. What is resolution? The act or process of resolving, such as analyzing a complex notion to simpler ones, the act of answering, as in solving, the act of determining. You have data. A massive amount of data. Across a significant number of sources. There can be millions, if not billions, of observations of entities within and across all data sources. Some of these entities are described differently but are the same, while others are described similarly but are actually different. Entity resolution is recognizing when 2 observations relate to the same entity, despite having been described differently. Conversely, it also means recognizing when 2 observations do not relate to the same entity, despite having been described similarly. Advanced concepts in entity resolution. Entity resolution works best when records contain a full name and at least 1 additional feature, such as an address, phone number, email, or other unique identifiers. The more features on each record, the better the entity resolution and relationship linking. These are all examples of entities. An entity, like a person entity, contains information in their records like their name, their date of birth, a home address, and their cell phone number. These are all examples of features. A given feature, like a home address, contains attributes like city, state, and zip. Where you have multiples of the same feature type, like address, you would use a label, like mailing in the case of a home address, and employer in the case of an employer's address. Features shared by entities create relationship links automatically. You can also disclose relationships. Senzing Entity Resolution enables rich network graph visualizations of discovered and disclosed relationships.
What we're going to do is we're going to watch Jeff Jonas present entity resolution in slow motion. So this is a bit of a pop quiz. So, and Jeff will explain to you why. So for those of you who've been very familiar with Senzing Entity Resolution, here's your test. For those of you who are new to it, this is going to help you create a picture, an animation in your head about what's going on in the engine as it's seeing records. And then we're going to enrich that understanding as we continue.
Now, for fun, I'm going to show you something I call entity resolution in slow motion. Think of it as a little master's class in entity resolution. Now, I spent about 30 hours making the next 10 moves. It's going to go kind of quick. It's going to feel like a little quiz, but let's get started. Here's 3 records. Imagine these come from 3 different systems, or heck, the same system. Are these the same people? Or is it 2 different people? Or is it 3 different people? Now, if we're all in the same room, I'd have you show hands. You'd be surprised how many different answers there are. But the answer is really they're the same. And we would call this just the most simple fuzzy matching. The name, Rob, Bob, Robert, the addresses, the phone numbers are structured different, and the month and days are different. The date of births are different, but only the month and day because they're transposed. Well, what if you got somebody that comes along with the same email? Well, often that's the same person. But sometimes husbands and wives and sometimes whole families use the same email. So in this case, you'd have to call that a separate entity and a discovered relationship. Now, while I'm mentioning discovered relationships, I'll just mention you can disclose a relationship as well. Here, you learn that Kim has a spouse who's Rob in the upper right corner, record 3. You didn't have to guess. She told you when she signed up or onboarded for the bank account who the spouse was. Now, so that's the disclosed relationship. So, record 6. Compare this to record 1. What you'll see is the names are close and the date of births are the same. Same person or not? I'd ask you this question. Would you say it's the same person for sure or just a good chance? Now remember, a rule about this is you have to favor the false negative. Only put them together if you're sure. So because of that, we would call that a possible match. So you're graphing it. There's a very good chance for the same people, but you don't know for sure. Now, here comes record 7. What would you do here? Compare it to record 1 and 4. Same email. How would you know which one it is? You know, most record matching systems or entity resolution systems would arbitrarily attach this to 1 or 4. What if record 7 said something like, you know, keep an eye out for this person, or they're a high roller? Would you really want to just arbitrarily bind it to record 1 or 4? What if record 7 just had the word street on it, so it made a little bit more like record 1? As if Patricia doesn't live on a street. The right answer, and we call this a special kind of possible match, it's called ambiguous. It could be either. What's interesting about this, by the way, is if record entity E2, record 4 didn't exist, you could be darn sure record 7 was entity 1. And if entity 1 didn't exist, you could be pretty sure it's entity 2. But they both exist. Funny and true story. George Foreman, the boxer, named all 5 of his boys George. This is a case for ambiguous. If you've got George Foreman with a home address and a home phone, it's going to turn out there are 6 people with the same name, home phone, and home address. Now it's going to get a little more interesting. Take a look at record 8. Now compare it mainly to record 2. Name good enough, address good enough, same phone number. So record 8 is going to become part of entity 1. I'll just give you the hint. But something else is going to happen, because the moment record 8 snaps into entity E1, it's going to learn this email address, bsmith@work. And do you want to take a guess at what might happen next? In real time, if you're doing real entity resolution, the possible match 6 goes away. It converges and it pulls in because you've just learned enough about entity 1 to know. That's a fantastic thing, because in very large systems, you might have hundreds of thousands or millions of maybes. And in this case, a future record fixes a prior maybe. Now this one's even trickier. Record 9 shows up. Compare it to record 3. The name, good to go. And the driver's license or passport number, whatever kind of ID it is, good to go. Yep, man, record 9 and 3, they belong, those belong together. Hey, but wait a minute, look at record 1 and 2. The date of births are different by a big distance. And notice that record 9 has the word senior. Oh, isn't that interesting? So I'll tell you, record 9 is going to appear over here to the right of entity E1. But then I'll ask, what else do you think should happen? And in real time, when record 9 lands, it has to change its mind about the past and pull record 3 out. That was a false positive, by the way. This is an example where there's plenty of evidence to put them together. But alas, just like in a puzzle, every now and then you learn something and go, oh, I could have made a better decision in the past. And by the way, the relationship moved from E3 to E1 to the new E6. Now this, it turns out to be hard to do at scale. Imagine your organization has already ingested 1 billion records, and this record 9 was the record 1,000,000,001. Imagine this, you have to say to yourself, now that I know that record, number 9, had I seen that in the beginning, before I'd loaded 1 billion records, over the 1 billion decisions I've already made, would I have made any of them differently? Doing that in real time, using new observations to reverse earlier assertions, is hard to do at scale. We've spent like millions to do that. If you can't do it, there's this really interesting consequence. Let's say your database is 1% wrong because of errors. If you can't fix the past, accuracy begins to drift. One big data aggregator, a name you would know, told me that their database drifts in accuracy 1% a month. So here by March, the database is 4% inaccurate because a new record came in, he didn't fix the past. And what is normally done is you have to reload everything and it cleans it up. And then over the next quarter, it is just drifting again. And then at the end of the quarter, you tear it down and reload. These are a form of unstable systems in the sense that every quarter or month or day, you have to rerun all the history to bring the accuracy back. Now contrast that if you can fix the past with new observations, where new observations reverse earlier assertions. I use the term sequence neutral. Did you get record A first, then B, then C? Or did you get record C first, then B, then A? So if you do this, where you fix the past in real time, it's a style of real-time learning that is not really talked about. You don't end up with 4% of errors over a quarter. Imagine if you're trying to protect a border or a country and keep a terrorist out, or a money launderer out, or refund fraud in a retailer. Imagine being that wrong and having the wrong answer and only realizing it after you reload all your data. You know, a funny thing about this, actually it's not so funny, is many of these systems that operate this way that are batch and you have to do full reloads use an enormous amount of extra compute. Because while you're running the real-time system here, you're spending like, 24 hours or all weekend reloading the system on a whole separate infrastructure. It turns out if you're real-time and sequence neutral, it's greener IT. You, in many cases, need half the hardware and much less compute. Okay, just a couple more moves and we'll move on with the graduate class. This one, I like a lot. Okay, look at record 10. Now, if we had a lot of time, I'd have you study this and tell me what to do with it. Most people would say it belongs on its own because it doesn't match record 1 enough, just an address. And it doesn't match record 2, it's just a phone number. It doesn't match any record other than a few features, but not enough. But if you knew that record 1, 2, 6, and 8 were all part of E1, you'd realize record 10 was the same. Most entity resolution systems do record matching. Because it doesn't match any individual records, it can't match entity E1. But in fact, it does. We call this entity-centric learning. And a few systems out in the world do this, but I'll tell you why it's so important. It's really important with messy data. If you have lots of sources and lots of messy data, lots of messy marketing data, for example. But there's another reason it's so important. My team and I have been using entity resolution for years, all the way back to Vegas and since, helping organizations try to flush out bad actors, people laundering money or human trafficking or counterterrorism. And here's the thing that's true. Across the entire spectrum of bad guy hunting, there is a single primary deception tradecraft. I call it channel separation. Here's the rule. Nobody, no clever bad guy, uses the same name, address, and phone on every record. Like only the idiots would do that. And you don't have to worry about them because they run out of gas on the way to the operation. They take a wet match to the fuse. But clever bad people don't do that. We helped a big global bank. They had a customer that they ran off for money laundering, but because of entity-centric learning, we showed them that they had 5 other bank accounts at the bank that they didn't realize because of channel separation. And if you want to catch this kind of bad actor, you have to be able to figure out they're all the same person, despite the fact each record didn't have enough info. And entity-centric learning does that. I think just 1 or 2 more moves, but with GDPR, you have to be able to delete records. Well, if you delete record 8, you have to be able to unlearn, and you don't want to wait a quarter to reload. If you delete record 8, you have to unknow that record 6 was you were sure about, but has to go back to a possible match. And record 10 is now just a relationship. By the way, you have to be able to do this in other languages and other scripts, and entities can be companies, not people. Heck, they could be vessels.
Let's talk about the life cycle of a record as it is evaluated to become part of an entity, as well as other behaviors that happen in the engine. So you'll find this in the entity resolution process white paper found in your study packets. So Jeff, if you will, tell the story of what happens as a record enters the system and goes through the process of becoming part of an entity or changing what is known about entity relationships, or what is about entities themselves.
Yeah. So the first step is receive and process records. And, records, entities consist of features. Features have attributes. So when we receive a record and it's got an address on it, we're going to standardize that address and put it into our feature library. So what the feature library is the name Jeff Butcher has got an ID. The name Laura Ulmer has an ID. The address 111 First Street has an ID. So once we see a value like that, it goes into our feature library and is given a number. So we only ever have to standardize that feature once. And then any entities like in the record library on the left, it's just a pointer from a record number to a feature number. And that is just a structure that keeps things fast. But if you're looking at our database, you're going to see a feature table, and you're going to see a feature link table, an entity feature link table. The compute new features, that is the process of creating keys. There might be 10,000 Joe Smiths in your database, and 1,000 Joe Smiths in your database, and 10,000 people born on 12/15/2005. But how many of those Joe Smiths were born on that date? And that's a much smaller number. And that's the number C on row 1. That's compute new features. That's where we're creating the keys that we use to find records. And we create a lot of keys. name and postal code, name and date of birth. And when there are, multiple tokens in a name, like, Robert Jeff Butcher, that's my first name is Robert. So we would create a Robert Butcher, born on that date, computed, we compute that feature. They're called expressions. We're expressing the records or the features in certain ways. So Robert Butcher and my date of birth, Jeff Butcher and my date of birth, Robert Butcher and my postal code, Jeff Butcher and my postal code. And those help us find candidate records within the billions of records that get loaded and help keep entity resolution fast. So once we have a complete view of the incoming record in one, we'll go on to two, and we'll take all those raw features and even expressions and find candidates. So when there's, so the Jeff Butcher comes in who lives at an address, we might find 10 records with Jeff Butcher. We might find 20 records with that address. We might find 4,000 records with that date of birth. Well, we can't bring all those 4,000 records in, so we skip the date of birth alone. And then, so the records that we found by my name and the records that we found by my address, there might be some delta between, or some cross between the two. So we've got maybe 25 total candidate records that we need to look through. And then we go through step 3. And step 3 is where we use our fuzziest logic. So maybe we didn't find one of the records by my name, we found it by the address. But when we apply fuzzy logic, it's Jeff Butcher versus Robert J. Butcher. Well, that's pretty close. So the address then gets a score. I'm in step 3 if I didn't make things clear. We're comparing features. So we've got all these candidates, and then we score all the features of all the candidates, and we find candidate 1 has a name score of 20, or let's say 90, has an address score of 100, and has a date of birth score of 2, right? So that means it's a name and an address minus a date of birth, and that's where we're applying principles. Once we have all the scores, we apply the principles. The principles say, if you have a name and an address, but the date of birth is different, that's not a match. It is a possible match, though, or possibly related, depending on how close the name is. Maybe only the address is the same. So, and we take all the candidates and we apply all the rules to all the candidates. Well, I'll say it differently. We apply the best rule to each of the candidates. So we might have 2 candidates that hit a resolve rule that say that they're, well, I'm going to back up and say we might have 1 candidate that hits a resolve rule, meaning that they are the same person, and 2 candidates that hit a possible match rule, and 4 candidates that hit a possibly related rule. And the rest of them, just they didn't score high enough in anything, so they're dropped on the floor. They were not good candidates anyway. So then we update our graph. So now we know 1 more record about a person, and we know their relationships. So then we get to step C of row 3. Did we learn something new? So we loaded, or we found 1 resolving candidate. And when we look across the features of what we knew about that person before, or that entity before, we look to see if we learned anything new. Maybe we matched on name and address and date of birth, but the new record has an additional phone number that we didn't know about before. So that's in C on row 3. And if the answer to that is yes, we go back through and find new candidates again. And we keep doing this until we learn nothing new and we're set with our entity. And then we do step 4, where we update the database and respond with any outcomes. So if you're that respond with any outcomes, what comes out of that is, maybe you loaded customer record 1, 2, 3, 4, 5. What could come out the end on number 4 is entity 1, 2, 3, 4, 5 got resolved to customer record 12345 got resolved to entity number 46. And that's where your real-time process would take over and say, what do I know about this? What do I know about this entity? Are there any good data sources versus bad data sources together? And is it something that I want to alert somebody about? So that's where we get to the respond with outcomes. That respond with outcomes is something that, we were talking about earlier. You would configure what you would want to happen. And when you're loading, 100 millions of records, you're probably not going to do the compute of, any insights. It's not real time. You're just trying to get the history in. But when you are real time, that's when you would do, more of the real time alerting.
We've now completed our first section on Sensing Entity Resolution. We covered what entity resolution is, what is needed in data in terms of features in order to perform entity resolution, demonstrated entity resolution in slow motion, and began to cover how records are processed to create entities and link relationships. In our next section, we're going to go into depth on the entity resolution process and principle-based entity resolution details.